So without further ado, I'd like to introduce the CEO of OpenMP, chair of the Transactional Memory Working Group, Canadian rep of the ISO Committee, and also the creator of user-defined literals, Mr. Michael Wong.
Right on.
Thank you. Thank you, Charles.
Yeah.
Hello there in TV land. Hello there, everybody. Can you guys hear me reasonably well?
Yeah.
Thank you. Thank you. So my talk is going to be a lot more about C++ 14, the upcoming standard. And obviously, I've kind of put a little bit of cute title on top of it, but that's okay. I think you guys can understand where it's going once you see it. I kind of look at it as being something that comes after C++ 11. C++ 11 potentially might have taken us down the rabbit hole. And here, we're going to step through the reflection and see where we're going to go. Okay? Now, it is interesting, though, because a lot of this talk, I have to say, is from the contribution of many, many people throughout WG21, throughout industry, academia, meaning I've stolen a lot of this stuff from many, many people. I've even stolen this disclaimer, actually. So, however, I do want to tell you that I still want to claim all credit for any kinds of errors, stupid mistakes. These are mine. They're all mine. No one else can get them. So, what follows is going to be a bunch of IBM stuff, which I'm going to quickly skip over. That's just the way I am. I'd like to talk a little bit about move capture, literals, lambdas, deductions, and digits, not necessarily in that order. And I might not even finish it all, but I'll try to cram as much of it down your throat as I can. So it is interesting following different speakers, and as Scott said, I totally sympathize when you said looking at the different styles. I just, like you, I'm awed at being here with the various different speakers. Andre, a man I've admired for many years, he's probably invented more templates than I've ever actually read. That's how far ahead he is. Anytime Herb talks, I feel relaxed, coming out of it with wonderment that C++ is going to keep going. I always get that sense that I'm going to come out of it feeling really good. And of course, who can beat STL? I mean, I know that you've actually deliberately slowed down from light speed, which makes it understandable. And of course, I can't forget Scott, because when he's talking about no except, I actually thought about what no except really is like in my mind. I think about no except as something like, it's as if you had a boss that told you that if you do a crappy job, okay, have an exception, just don't tell me about it. Because if you told me about it, I'm going to fire you. As long as you don't tell me, things will be okay. And there's almost nothing I could really say about Bionic that hasn't been said. The man speaks for himself. So I think I'm going to go on and take a look at what we're going to talk about. So obviously, C++ 11 is ratified, but I am actually missing fingers and toes. Well, what are some of those? Well, it looks like that you can capture by copy or by reference, but why is it that you can't have move capture in lambdas? You created a bunch of this design called user-defined literals. But how about some actual real user-defined literal suffixes? There are none out of C++ 11. We absolutely love monomorphic lambdas, which almost supplants std-bind. Okay? But why did you stop there? And if lambda returns can be deduced, why not normal functions? And then finally, can we get some kind of digit separators? So these are some of the things that I intend to talk about. Whether I actually get to it or not, well, we're going to see how well I manage. So here, take a look at this. This is actually one of the themes that Biano put up, and I absolutely loved it. The idea is to absolutely compute less. So 1983, where were you in 1983? Just to date myself, I was actually entering university. Okay, so around that time, it turned out that there was an Air Canada flight. That was a Boeing, and I know there's a lot of Boeing engineers here, and I didn't put the slide in because of that, okay? It was a 767, and it ran out of fuel at 41,000 feet. Can you imagine the sheer panic when that happens? Miraculously, there was no fatality. The plane glided to a landing in Gimli, Manitoba, and that's the plane there. That's why it's now called forever after the Gimli glider, okay? I won't go too deeply into all the heralding events that happened. Let's just say it was a miraculous landing. What happened was that instead of 22,300 kilograms of fuel, they had only 22,300 pounds of fuel. That's about less than half of what they actually needed. Okay? And essentially what was going on is, without going into airplane details, sometimes it's kept in volume, and sometimes it's kept in weight. So there was always between the ground crew and what gets loaded up. So there's always a need to always have this conversion factor. And of course, Air Canada at that time had just switched from imperial to metric. And the conversion factor was 1.77 kilogram per liter that they used. Wrong, because the real one should be 0.803 kilograms per liter. And you can imagine what happens after that. 1999, almost 16 years later, the Mars Climate Orbiter, I think you guys all know about this one, costing over $600 million, was lost due to navigation error. And the software error was that it was another one of those metric units in the ground software. There was a difference in terms of the thruster performance data, which was kept in imperial units. The end result was that it crashed. But the greater result of that damage was that it lost the lifetime work of over 200 engineers. The mission data, scientific data results. And the thing is, it feels so needless because ever since high school, we've all been taught that we should take unit computing into account. Okay? So why don't experts do that in their own field? Well, it turns out that very few mainstream programming language actually support units. And why not? Because it's actually not that hard, because most language that I would know of can encode some sort of value quantity pair, some sort of quantity unit pair. It's not that hard. It just takes a little bit of memory, a little bit more computation to do the conversions. Okay? That's probably, as best as I can think of, is the reason why people don't do it. It doubles the size of your data, and checking in every computation would double the cost of the performance. And of course, for things like spacecrafts and airplanes or maybe cell phones, they are problematic. So if you could save, you do try to save. Okay? Now, the problem is, what's the solution that people generally follow? They try to keep this unit in their head. They write it down in documentations, maybe in comments. The problem is that the compilers don't actually read these things. Not yet. I suspect that will happen at some point. Okay? So why don't we support units? If a number actually crosses an interface without its units, it's going to take on a brand new meaning. And in this case, in the Mars orbiter case, it changed by 4.45. In the Air Canada case, it was halved. Okay? So the problem is that the integers and floating point numbers are basically unsafe interfaces. And so when it comes down to it, why don't general purpose language support units? It can't be because it's hard to check at compile time, because it really isn't. It's mostly historical. A lot of different reasons. Maybe the different unit systems, the markers are not needed. You can't really build in every possible notations in your language design. And the designers have to choose one or the other. And in most cases, the designers choose to do nothing. Okay? So in terms of C++11 unit programming, what we would like to do is have some sort of specialized tool or language that supplies the SI units. And the feature basically works best when it's integrated into the general purpose language. Okay? There's a sufficient amount of reasons for this that I think defining unit speed as a template and a unit part with quantity is sometimes not the best way of being the most expressive things you do. Because this is what it ends up looking like. And this is actually from Biana's 2012 keynote. Okay? And it's one of the seminal paper that he's written. Well, essentially, he's shown a way of writing units, not the only way, mind you. This is one of the common ways you could do. You could encode your units as an enum, okay, and then instantiate it so that it has the right particular value for the type of unit you would actually use. Okay? It does get a little cryptic as you follow along, though, because as you get to speed 1, where at the bottom there, where it says meters per second, it's getting to the point where it's almost unreadable. And if you add any more units to that, it's going to be it's going to get even uglier. So I'll just show you a quick flash of what C++11 user-defined literals look like. Okay? It's actually a fairly simple concept. and I'm going to talk about it at some length. But essentially, you can sort of look at this, and you can start seeing, compared to the previous code, I can see that at the bottom right, ignoring the stuff on the left, which I've set up to create a bunch of literal operators, I can now create an acceleration of which that tells me that it's going to be something like 1 over 0.5 per second, meters per second. Okay, I think I have a spelling error there. Okay, but let me dive into it a little more. I think the whole point of this is that we want to enable some kind of a type of what Bionic calls type-rich programming at compile time. And out of this is that you can improve your code quality without additional runtime costs. And I'll show you how that's done. What it means is that you want to use a static type system that moves checking to compile time. This is a theme of C++ for a long time now. You want to move as much as possible of the computation into compile time, and that way you can avoid all these kinds of ugly macros and C compile pre-computed magic numbers that goes along with what's going on in other kinds of languages. And certainly, there's the future benefit of something like this is that there's no race conditions, because there can't be any race conditions on constants, right? So I'm going to take a look at what literals would mean, okay? Probably the biggest motivation for creating user-defined literals is because we want them to have the same kind of flexibility as classes. Classes are extensible. Literals themselves should be extensible. Before user-defined literals was created, there was only two ways. There was really only one or two kinds of literals. They were the 2's complement literals, okay? And depending where you are, you might also get some hexadecimal floating point literal. That may or may not be there. What this says is that it allows us to create a new kind of literal that fits with whatever the classes that you need. If it's SI units, a new kind of string, maybe some sort of arbitrary precision integers. The real cause that motivated us in terms of asking for something like this was what's called decimal floating point. This is financial data that needs to be absolutely accurate and don't lose the precision that 2's complement floating points do. So what happens is C has already have something called decimal floating point literals. They put it as a built-in type. In C++, we actually chose to put it in as a class, as we would with something like this. No argument there. But in order to initialize it, you have to call these fairly ugly constructor syntax. It doesn't look like you're actually initializing a user-defined literal. With UDL, you could actually write fairly natural syntax that looks like you're initializing a user-defined literal. Okay, and that's where the solution lies in. In terms of the rules, you can pretty much use it for any kind of built-in literal without a suffix, and you can concatenate it with any kind of identified suffix to be a new literal. So you can use 23 is okay, but you can't apply it to something like 23LL. Okay, now. And then the following group is trying to tell you that with UDL suffix, it's basically just an unqualified call to a new kind of literal operator. And one example of that literal operator is this, where essentially you have X operator, double quote, followed by the suffix of your choice, and then the parameters, the data that you're going to go in, that you want to put in, that you want to eventually convert. Okay? X is the arbitrary return type. Could be anything you want. Suffix is some sort of identifier literal suffix mapping to this call. And parameters is, we'll talk about that a little bit later. Okay? So cool. Can it handle prefixes, or both prefix and suffix? No, it can't. Okay? So it isn't going to be able to reproduce something like a hexadecimal floating point literal, where you have both prefix and suffix. It's not going to be able to do a binary the way you would do if you were to put it as a suffix. Okay, it could do it as a prefix. It could do it as a suffix, and I'll show you how I've done that. And of course, people might look at that and say, okay, so how many actual user-defined literals are there in C++ 11? Well, exactly 0. And the reason is because we pretty much said, let's put it in first, and then as time goes by, we can start adding the kind of user-defined literals that we would need to support the standard library. Okay. And by C++ 14, there was enough usage experience, there was an implementation that allowed us to add in user-defined literals. And and hence the lead-in as to why I want to talk about how user-defined literals work. The rules for the users is a little bit more subtle than what the library is allowed to do. You can only use suffixes with underscore, as is normal with what the user space can invade. You can't actually create ones without underscore. So for instance, 32.5 underscore kilometer is a user-defined literal. If you're the C++ standard library implementation, you could actually create it without the underscore. Underneath, what this thing is a bit of a syntactic sugar, calling operator, quote, double quote, underscore, kilometer, passing in 32.5 as a long, okay? And what it is it essentially takes as the longest thing, the type of it, I'll show you later on, is actually a long double, and it's going to take the longest string that you can take and whittle it down to whatever it is that you happen to need, okay? The actual code, and I wrote a kind of a pseudocode here, it's going to look something like this. Inside the operator, you're going to say const expert kilometers operator, double quote kilometer, and inside you could return something that takes a double, static cast it to a double, and then return the result. Okay? The thing that user-defined literals here is trying to do is take a normal literal that's been cooked by the compiler already, it has the usual meaning, and either transform it, maybe convert it from, maybe kilometers to miles somehow, transform the value of that literal, okay? Or somehow reduce the length or the strength of it or the representation of it. Yep, go ahead.
Does it have to be a constant expression?
No, it doesn't.
Call a function there.
That's right. And the subtle difference is that if you don't put const expr, it's probably going to run at runtime. Okay. What we did was we wanted to enhance it so that it has the ability to be ROMable, so that it could be done at compile time. Okay. Const expr, though, even that doesn't guarantee it. I have to subtly warn you, because if it throws, that's not going to be done at compile time. Okay. There's one other thing that will make it happen, and I'll talk about that. But here's some more examples: kilometers, distance, 32.5 kilometers. You can have 19.2 underscore mile because I'm doing the conversion inside that operator function. Okay, I don't exactly remember what the value multiplication is, but you can imagine. You can add them together in this case. You could add underscore miles and underscore kilometers together because more than one literal can return the same type if you convert inside and define operator plus. You can build mixed built-ins, string literals with UDLs. So here in the next example, I can actually concatenate these two literals together, okay? And so I'm going to go a little bit deeper and look at what are the different ways you can do user-defined literals. There's what they call the raw group, the raw literals, and the cooked literals. And what I've essentially described for you is the cooked literals. Just to recap, the gentleman actually asked me if I have to put const expr in, and I just want to make sure people can hear that. No, you don't. Okay, and that's for the TV land out there because they might not hear you. Okay, and later on I'm going to show how we can guarantee that a user-defined literal can be done at compile time. And const expr is one of those ways, but it's not quite enough as it turns out. Okay. All right. Here's some cooked string literals, okay? And the way we do it is, this is an example, and in this case, I've actually used a wide string, okay, wide character string. And I can take something like a localization, internationalization string, and convert it using the underscore ws suffix. And this would actually call the operator that's been described above. With cooked string literals, they can be concatenated like any other string literals. Okay, as long as all the components are the same suffixes. So here, even though this is a wide string character, okay, I could concatenate that with the normal string. Okay, that's allowed. But I can't concatenate something that has an X suffix with an S suffix, for instance. Okay, that makes sense. So what does the compiler do when it looks at these kinds of cooked literals? Right now, what it does is it goes through when it sees a number, a literal, it goes through all the possible suffixes to see if you hit them. Is it a floating point? Is it a double? And when it can't find any of those in C++, the C++ 98 compiler, of course, abandons the lookup and hits an error and generates an error. Now, what you do is instead of hitting that point, instead of going to the error, and before you go to the error, you go through and check all the user-defined literals that you can see. And if you can find one of them, then you can apply that. You can apply that user-defined literal, put that operator in place, and then make your call afterwards. That's all it is. Implementation is fairly easy to imagine what it would be like. And in fact, this has already been implemented in GCC as far as I know. Unfortunately, I didn't check Clang because I know that's going to come up. But I think it probably has. I'm pretty sure it did. We did. So there are a couple of forms for the cooked literal, and just remember that they take precedence over the upcoming raw form that I'm going to talk about. Okay? There's a form for unsigned long. There's a form for long double. This essentially covers your integral and your floating point types. The sign is a unary prefix operator, so you don't need to account for the negative sign because it's actually an operator. Okay? People who are in the compiler building business generally know that. Some of you may not if you're not in the business. And then the form for the character string is normally what I've shown here, const char star, with a size underscore t for the length so that you can keep track of how long this thing is, because there's probably some kind of memory allocation that needs to be done. And you need that length to tell you what it is. And then, of course, it can accept all the other kinds of Y strings, char 16, char 32 strings, if you send it in with the right prefix here. Okay? And as I said, the number of characters is passed as a second argument. Then there's the same variant for the char type as well, too. I won't go into that. And like I said, it's still essentially runtime evaluation. It's just a call. So what's the problem there? Why did we invent raw literal forms? Well, sometimes the cooking of the literal takes out too much information. For instance, if I want to use 1.2e minus 3 decimal float, that is really not the same as 0.0012 that you would write, because that's a 2's complement, and it probably isn't 0.0012. It's probably 0.0011999999 to some infinite precision, right? That is not what 1.2 e minus 3 decimal float is. It's exact. For banking calculation, I'm sure you've all seen the Superman movie. I don't know if it was the Superman movie where they collected all the little bits of coins or things like that, but it was some movie. That's why these are different. The cooked form that comes out of 0.0012 loses too much information, so that in that case, you really want to revert to a raw form literal. And a raw form literal has much more chance of being done at compile time. Here's how you do it. Okay? You can transform the raw form of numeric so that if it's float or integer, there's no character string version of the raw form. It doesn't make sense. Just think about how you would change the character representation, right? It can't be done. And what happens is they're basically needed whenever the UDL suffix changes the meaning of the digits in the literal. Okay, so in the form here, there are actually two forms. One is what's called the raw literal form, and it's just using X operator, double quote suffix, char const star, and this is how it disambiguates from the cooked literal form, because it doesn't have a length in it. But again, I'm not actually asking for character strings. I'm asking actually for the representation of the actual numbers that in a character form. And this is still not going to be compile time done at compile time if it throws. The next one have a much greater chance. It's actually your friend variadic templates. Okay, it uses a pack expansion, and I think you guys all have the shirts. Okay, where there's a parameter pack in the front and there's a pack expansion in the back, and that's what you're going to be doing. You'll be unpacking these parameters, working with each of the digits one by one, and all done at compile time. Okay. And if you use it right with a variadic template form with some sort of with constexpr, then you and with some sort of template meta programming, then you will be able to achieve it for compile time value. This is about all the templates that I actually know, Andre. There are some compile time constant tricks that you do have to learn. To ensure the compile time evaluation, like I said, you have to use the literal operator template. They have to be implemented using recursion. Okay? The error checking at compile time generally has to be done through a static assert. You can't throw. Okay? And of course, it uses unpacking of parameter packs to build a new value type. And the performance can be somewhat questionable depending, because there's a lot of instantiations going on. Okay, so depending on how many of these literals that you're firing up, it could really pick up your compile time. And in a way, that's actually one of the key motivations of why in C++ 14 we have introduced a built-in binary type, which I'll talk about, which is actually the whole reason I've spent almost 30 minutes talking about this. There are some idioms and guidelines, though, when it comes to using user-defined literals. Okay? You should know that they use built-in types and are never, ever found through ADL. So it's kind of tempting to put them in the global namespace, but don't. Don't define UDL operators in global namespace, because everybody will collide with the suffix. Imagine how popular the suffix S is, okay? Or M or CM, because they're single letters. The committee worked hard on this, trying to decide how to make it so that it's fairly easy. And the idiom is not too bad, although some people might disagree with it. Basically, don't ever have a global using declaration, because you're just not going to know if literal operators that you pull in from one namespace with another, and they both happen to have the underscore US suffix. Is that really a microsecond, or is that US dollars? They're both going to be numerics. Okay. And they might both be using floating point types. What you want to do is surround it with namespace and then further nest the namespace to specify the literal operator in your own header. So don't use a using declaration in your header to import the literals to the global namespace. And also ignore my suggestion that was written in N2750, the original paper, that says add the using directive in the same header. In the same header file, which effectively does postpone compilations, but it's still ambiguous if you have two libraries defining the same suffix. Instead, what we'd like to do now, based on current knowledge, is that you want to add a using directives so that you can import the literal that you want, or a namespace declaration for the operator that you really want. Both are perfectly fine. This is not an eye test. You could actually write a binary user-defined literal, and Daniel Kriegler has done it. I'm going to leave the code in the slide so you can look at it later. We're not really going to actually analyze this. But he did write a fairly nice set of user-defined literals using the idea of both using a templated templated raw operator, as well as a pure raw literal operator. Okay, so the result is that it's gonna work out. The one line in red is just saying that it doesn't change type, but it could. That would just be a little more code. So here, even though that I could actually stuff the whole thing for type I into an unsigned in, it's still being stuffed into the longest thing possible. But that's okay. This is just a first implementation. It's an easy implementation, and the code is fairly easy to understand. Okay. But you can see that all I'm doing is testing to make sure that the values comes out the same. Otherwise, I'm going to claim ouch. So with user-defined literals, what happened was the proposals started coming in for C++ 14 to see whether we should add all kinds of suffixes. One of the first ones that was asked to be added was whether we should add underscore B as a binary user-defined literal. This would be useful for the library. This could be something that could be done in the C++ standard library. You wouldn't need any compiler magic to that. As you can see, I've already got code that could do something like that. There was discussion at the standard committee level whether this is the right thing to do. And in retrospect, it seems that many people felt that given that hexadecimal and octal all have a prefix, putting a B as a user-defined suffix doesn't kind of work well. So it's probably better to put it as a prefix. Well, that would mean a language change. In this case, it's probably worth it. Because as you can see, I've already shown that having too much of these instantiations can actually really slow down your compile time. However, the compiler can do it without any of that cost, incurring any of that cost. So now you can have, yes, it is true that you can have user-defined literal that looks like what's on the left side, but that's not what you got. Okay? You're going to get something that's what's on the right side, where you can say, well, all those numbers essentially are exactly equivalent. And the last one is the user-defined literal, the way it would look. Okay? In C++ 14, we've also added other kinds of literals, not just binary. So beyond this, the rest of the package that was proposed did make it as a user. Oh, yes, go ahead.
That's not user-defined, that's compiler.
That's compiler. That's right. So the question is, that's not user-defined now. That's compiler. That's exactly it. On the left side, it would have been user-defined, okay? Or in this case, really library-defined, because a library could put a B as a suffix. But on the right side, what you end up getting for C++ 14 is effectively now a prefix, just like 0x, just like the octals, okay? I think there's a uniformity here that makes perfect sense. So that's why I said, we were wondering, should it be B or not B? So along with the package of binary, they also proposed the idea of user-defined literals for strings and for time. And those did make it as a library addition. And because it's not a user-defined literal, it's a library-defined literal, you can actually drop the underscore. So the idea there is that what we've done is we created an inline namespace for std literal for all such user-defined literal namespaces. We're going to end up overloading operator s for double quote s for std string and for chrono duration as second. They don't actually cause a problem because one type is going to be a string, and the other type is going to be a numeric. Okay, so it's okay. There was some controversy around the idea of whether S really should work as a string, because string is really a class. It's not really a string. It's the standard library class, isn't it? And there was some concern that there's this idea coming out called string underscore ref, which sometimes people call string view, which is truly and actually dereferenced library string. That might be more appropriate to be called to deserve the suffix s. As a collective group, we kind of decided that when that comes out, they can create something called SR, SV. There's just been too much history wrapped around the idea that S is a string. Rightly or wrongly or not, that it's not really a string, there it is. Okay? So in C++ 14, you now have these, you will now have these UDL suffixes. Std's basic string, suffixing S in an inline namespace called std literals, and here's the nesting of string underscore literals. And std chrono duration, which suffix all the usual ones you would expect, like h, like hours, minutes, seconds, milliseconds, microseconds, and nanoseconds, in some sort of inline namespace in the same pattern, std literals, chrono literals. Okay? So if you want to use it, I'll show you how to use that. But there's going to be more use. This is going to open the gate for more UDL suffixes for other integral types. And there's pretty much only the lowercase suffixes. We also had a proposal for complex literal types. We didn't push forward with that. There were some concerns. We're going to look at those. The namespace idiom is that all the suffixes for the user-defined literals are in separate inline namespaces below std literals. So if you want to import all the literals from the standard, you use using namespace std literals. If you want to import all the literals from the standard of a specific type, then you might say, using namespace, std, : string literals. Okay? Probably the best way to avoid clashing. Now, this slide is real, unlike the binary slide. By the way, I believe the person who proposed binary is actually in this room. I think James Dennett is here. James? Are you still here? Thank you. So this is real. What's on the left side is how you would want to use this, the chrono literals. Okay, so you would say 24H for hours, 45 min for minutes, and 0.5H for half an hour. Okay. Okay. Any questions? Yes.
I was under the impression from reading something about this, you're not supposed to use fractions, they're supposed to be units. You would say 30 minutes rather than half an hour.
Yeah, doing fractions is not going to be as easy. I believe that's the case. So the question was that he was under the impression, he read whether you can use this with fractions, okay, and that you're supposed to use actual decimals, okay, and I'm confirming that's what it is. Next question. Yes, Chip.
So the default for the chronos is the representation that's integral. So
Right.
I guess the chrono UDLs have versions both for long double and for long long? Because the default representation is maximum.
I probably would have to check the standard to see exactly what it is.
Cool.
Yeah, that's probably a fairly easy thing to do. Okay. So the question is the default both for long double and for both forms? Okay. Maybe someone can check the standard for me. Okay. Yeah, question up there.
So when I have 0.5
Hours.
if my operator took int instead of float, would it promote that to?
So the question is it going to have, I think this is what your question is it going to have an overload problem with both the int one and the float one, right?
Right. Or is there both, I guess?
I think if there is both, there is not a problem because they have different parameter types. Okay.
So it is able to do
Right.
conversion before.
Yeah. I'm guessing there's only one, but I didn't check to see if there was an integral one as well too. Then that's kind of what Chip was asking. Yeah. Did you have the answer?
Yeah, the standard does overload all of these chrono operators, both unsigned long long and long double. So all of these are unambiguous. You'll get integers if you said integer, you'll get float if you said float.
Okay. I'm going to try to repeat that. The answer is yes. They are overload. All the different, both long and long double are there, and they will become they're unambiguous as far as the call is concerned. Thank you. Okay. Okay, I want to just push on because I want to see how much of this I can get through. So one of the next thing I want to do is talk about how we make lambdas sing. And here is just a quick recap of what C++ 03 lambdas look like. And of course, moving to C++ 03, there is no lambdas. It's generally called a functor. Okay? And in C++ 11, we created the idea of a lambda and closure. And in C++ 14, we're advancing that idea to what's called polymorphic lambdas. C++ 11 variety is called monomorphic lambdas. I am actually not going to explain too much about this slide because I kind of get a sense that some of you guys already know about it. But I do want to walk through a kind of a quick scenario what lambda closures look like. Okay. Here, what I have is a basic caller, okay, initializing variables that's going to be captured and then used in a lambda expression. So starting out A and B, of course, is 1 and 2. And what happens is that in the call itself, as we advance this forward, A is going to be inside the caller, and because this is a reference capture, even whatever change we do is going to be reflected to the outside. So that the outside will see A equals 12, B equals 22, and the inside, of course, sees A equals 12, B equals 22. But if I make the lambda a copy capture, I would actually have to say mutable in order to make this change work. But because it's a copy, the change is not reflected to the outside. So the outside still says A equals 12, B equals 22, but the inside actually gets the new value. If I selectively set the lambdas, the lambda captures, so that the copy is on everything, but A I would like to capture by reference, as I do in the last line, then you're going to see that A will reflect the change from the inside, but B will not. But inside, I will see 37 and 29. Fairly simple, but I just want to get your mind around what C++ 11 lambdas actually do. And here's another one, starting with 42 and 15. Then what I have is I've created a lambda, which I'm going to capture by copy. It's a mutable lambda. And I'm going to advance it forward with multiple calls each time so that I'm setting the values for A, incrementing the values for B, adding up A and B into Z, and then returning Z. So A, even though this is a mutable lambda, because this is a copy, this is captured by copy, nothing actually will change on the outside. It always maintains the original values. Whereas the inside will keep incrementing, specifically with B incrementing from 16 to 17 to 18. And then Z's going to increment because it's going to be added up. I wanted to do this because I wanted to give you an idea how lambdas really work. And here's a slide I absolutely love because Herb had put this up in one of his talks, which I'm going to develop as we go along. What this is showing is what actually is the mental model transformation. Most of you probably know most of this, but this kind of succinctly captures how this mental model really translates. You always have your capture, your parameters, potentially, which could be omitted, your trailing return, and your statements. There's actually a little bit of stuff there, which I'm going to talk in between after the paren and before the return, but I'll talk about that a little later on. All the captures do is that they create this little private functor, which it's going to create a private member of all these capture types with the actual capture itself. And it's going to create a public functor constructor which initializes these captures through a member initialization list. Everything from the statement onward is just translated into this operator paren. It's just that in the second paren, you absorb the parameters that came from the outside. This is it. This is the entire mental model. It really makes it really easy to reason about when you look at all the strangeness about lambdas that ensues. So one strangeness we found in C++ 11 is this. What happens if the lambda is inside some class? What happens to the this variable? How is it captured? And it turns out that this is surprising because I think some companies have gotten bug reports that this is the number one thing that surprises people. Okay? It surprises me too. And Herb is one that brought this up to the standard, and I essentially duplicated some of his word here, where it says that one variable that can be captured without mentioning its name is this. It's almost invisible, but it is captured. It's captured by value implicitly, and because of that, the members are captured by reference. And you can see that in that code here, where f of x, where I have this embedded inside a class, and f of x is captured by value, y is going to be captured by value, because I said that in my capture statement with the equal sign. But z, which is a member, is going to be... It's going to be, because this is captured by value, z is going to be, and z is a member variable, then it's going to be captured as if by reference. That's pretty strange for most people. Okay? How many people find this kind of odd? Some of you, yeah? This is what it actually looks like if you break up that diagram. Now I'm inside of some class C. And what I've done is I've actually implicitly captured the this pointer, which, as you know, is what happens with any kind of functions inside. Okay? And it has a type of const pointer to C. I've also, as with the previous slide, I've also captured all the capture types. And I've created, as usual, the public constructor for functor, which, of course, takes the this pointer implicitly and all the capture types and initializing them normally as member initialization. In the operator, it's as if I have an operator paren function, which is a cons member function. So its type actually, for this type is actually a cons pointer to cons C. So this is what a lambda inside of a function. This is what a lambda inside of a class really look like. And because of that, this is the result. It's the next little oddity that we've been observing from C++11. Lambdas is automatically cons. You have to actually deliberately make them mutable. So here, inside of a val, I've actually created a lambda, which I explicitly said I want to make an explicit copy with my equal syntax. And yet I can't actually update val. It's going to be a compile error. Damn it, I'm actually really want to capture this explicitly, capture this by value explicitly. So I'm going to actually put the name val in there. And I still can't update val. Because the lambda, by nature, is implicitly const. Is this any better if I was to have some sort of regular function that take a count? Would you expect that you would not be able to update count? No, probably not. Okay. Because I'm actually passing that by copy. I should be able to update it. In order to actually update it, you have to add this mutable keyword, which comes after paren. And there's also other stuff behind it too, like exception specifications and attributes, but that doesn't concern us at this point. But as long as you put mutable between the parameters and the return type, the trailing return, then you end up creating this kind of a mental picture for your capture. Everything is the same as before. The only thing that's different is that it's now no longer a cons function, a cons member function. So the conceptual type is that it's actually a cons pointer to C. I love Scott Meyer's CPP notes. Who's read them in this audience? I'm sure many of you guys have. Okay. I think he abstracted out most of the rules pretty well in terms of looking at. It's basically a quick way to create a function object at the point of use. That closures basically outlive their creation function. So if you have non-static local they're only referenceable only if you capture them. Variables that have static durations are always referenceable. And we don't allow in fact, you're not actually allowed to capture them. You're prohibited from capturing them. You can select the capture mode defaults as I've specified here. You can access class members within a member function by through the capture of this implicitly. Lambdas without parameters may omit the parameter list. I actually want to make sure I ask Scott's permission for me to refer to his notes. He was gracious to allow me to do that. So one problem with monomorphic C++11 lambdas is that lambdas are essentially a hit. But come on, Miss Compiler, why can't you deduce my parameter type? You know exactly what the type is. I've been hitting this M key, and it's actually wearing off on my keyboard. I can't actually read it anymore. I really don't want to have to keep saying const iterator of something. So the standard has come up with the idea of, in C++14, allowing you to do something like that, where instead of saying exactly what the type is, now you can use auto. Now, this auto isn't exactly like the auto of auto type inference. It's actually more like the auto from template deduction. Okay? So, and I'll talk a little bit about what that might mean. But in general, this is what a generic lambda would look like, just to expand it a little more. In C++11, you have the auto. You can create a lambda, but you have to specify the type in the parameter, in the arguments. And it would create this unnamed lambda structure that I'm showing here. In C++14, it would look nearly the same, except it's using auto. And underneath, it would create this templated operator, paren, functor call. The template effectively gives this the ability to change into any kind of different parameter types. And this is what the picture looks like. Okay, you have captures, except now it's an auto param. your parameters has auto in it. And down here, the only transformation that's necessary is that it's now a templated type name of the various t sub i's that you would pass in. And then you would pass in the t sub I as a parameter list. Okay? It turns out you can do much more once you get past this. And I want to talk a little bit about move capture, but I don't think I'm going to have enough time. But I'm going to do about 5 minutes of it. Okay? Actually, yeah. So on Stack Overflow, people often ask how to capture a unique pointer by move for lambda in these situations. And the problem is unique pointer doesn't have any copy constructors. Okay, so it can't be captured easily. People have created all kinds of workarounds, like you have to create a unique pointer, you have to somehow wrap it up as a copy, and then inject it into the lambda in some way. Or people have even created wrapper classes that essentially chooses between the different qualities of unique pointer. All of these are kind of heavy workaround. One of them looks something like this. Okay. This is lambda capture workaround by Anthony Williams to make the lambda capture work for move only types. And the committee looked at this and felt that yes, there's a problem here, and they looked at the idea of being able to do lambda captures, but they took it far more than that. They created something that added generalized capture initialization so that it actually allows you to capture members that are initialized by arbitrary expressions. So it allows you to capture by move and declaring arbitrary members of the lambda without actually having any corresponding variables in the outer scope. And here's what it looks like. Here's an example of the new way of capture. X is now directly initialized by moving X. Y is going to be copy initialized by calling transform, and the rest are captured by value. This tremendously expand the usability of lambda expressions. And here's it's kind of a small code fragment to show you how you would actually do it. Underneath, however, and I'm going to try to finish with this slide, is something that says what move capture actually means. The transformation is quite significant because here what's happened is you've created a unique pointer type for your captures. You created a new functor constructor, taking in this unique pointer type as your parameter and initializing all the captures with a move of the capture. Okay? Everything else still remains pretty much the same. So I'm going to stop here because we're about 7 minutes. And I'm going to skip past all the deduction part and go to what's called a bike shed. So in C++14, one thing we tried to put in, but we didn't make it, is this idea of digits. So we wanted to put something in C++14 that allows you to separate digits. And this is a fairly common notion. You can have, typically in North America, the typical separator is comma, but in Europe, it's actually the opposite way around. And I've seen various forms. Some countries even use a single accent, single quote on top. So this was something that we tried to work on, and we spent a fair bit of time on it. The idea is to somehow separate those numeric literals, especially if it's long and hard to read, so that every 3 numbers is essentially, or whatever number you actually happen to choose. We didn't get it working. We couldn't figure it out because this is one of those things where everybody has an opinion. It's a fairly easily understood item, and everybody have their favorite separator. Just imagine, so three of the most common ones that we looked at was something like comma, and an underscore, and a thin space. And none of these work actually due to some amount of ambiguities that was discussed. What would you guys think? What would you suggest as a kind of digit separator? Anybody have any thoughts? I figure in an audience this big, somebody is going to have a better idea than what we had. We thought about underscore. Number one, it collides with user-defined literals.
Yeah,
Chip?
Not if you minimally consume the underscore.
Yes. And in fact, so the question is not if you minimally consume the underscore, but Chandler, please.
So yes, you can invent parsing rules which will allow you to disambiguate between different ways of consuming
This
the
is my
underscore.
Q&A, by the way.
And you can do that, and it takes a lot of effort, and the committee actually did it, and they debated about 4 different parsing rules, and they found one that they felt was the best compromise, and it has a really startling result. And I assure you, this was the best compromise. What it means is that, when you start writing units for, say, I don't know, like kilobytes of things, right, megabytes of things, it would look really nice. You have an underscore to separate your digits. You have an underscore for your UDL. There's no problem here. Until, of course, you hit an exabyte. And E is a hexadecimal character, a hexadecimal digit. And you can no longer disambiguate it. And so you end up having to have very weird syntaxes in order to have an exabyte suffix. And everyone's like, well, yes, but no one actually cares about exabytes, right? Like, really, who cares about that? Other than maybe, some people that work at small corporations that do care, who really cares about exabytes? And then we pointed out that actually the byte suffix of B is just as broken. Like, trying to use underscores leads to just hopeless amounts of confusion, trying to disambiguate in one direction or the other, to try and either get your hexadecimal digits or not get your hexadecimal digits and get your UDLs. It's just a nightmare.
Okay, I believe Biana is next.
Yes. See? This is how you get a byte shit discussion.
Anyone else? Shihao?
I think maybe we can allow to use a Unicode wide
Sorry.
quote there,
Okay.
single quote there.
Single quote.
Yeah, but
The
it's Unicode and wide.
Okay.
It's a different single quote.
That's really easy.
That works.
That says low.
Anyone else?
Yeah, over here. Yeah, I think having a different quote is a really, really bad idea because people are going to get so confused. What about period?
We already have a use of period, don't we?
Well, I know, but if you have 4 periods in your number, that's what they use period, and then they use comma for the last part in Europe. I see. Don't have a heart attack. I'm just kidding. No,
I know.
I think an apostrophe would be nice, actually.
I'm pretty sure Andre came first, and then this. Yeah, Andre.
Maybe just let the IDE split it up.
Sorry, who? Okay, so I'll come back to that. Yeah, go ahead, Andre.
Just payback time.
Okay.
Just a sort of a larger account. Maybe this is solving the wrong problem.
Yeah.
Because, so first of all, you spent a good amount of time discussing user-defined literals, and suffixes in particular, and I still have a hoarse voice after saying yesterday that -1, 0, and 1 should be the only constants anybody should use in a program. And this whole mechanism for representing magic numbers taken to a whole new level does seem to clash with the notion that you should not have so many magic constants in your code. And in fact, I wrote a bunch of scientific code, and they just don't appear that much. So why so much preoccupation for, I need to represent 100 meters divided by 9.8 seconds, which is like really fast for a human, but it's a magic constant nevertheless. So in my experience, it's good to have units, but having an extremely easy way of representing magic constants, which are bad, with units, does seem to be a sort of odd. I mean, it demands some explanation. Why so much focus on that? Whereas, to contrast, this is a real problem. So this kind of thing, where numbers like large numbers in literals are because 1 million, 1 billion, and 1 trillion appear quite sometimes in code. So that does seem to be a more worthwhile thing to look at. So essentially, this is payback time.
Okay.
And how do you comment about this demotivator?
I probably disagree in terms of which is the more important problem to solve, and probably that's ultimately the outcome of that. Okay, so yes, one suggestion is potentially get rid of user-defined literals, and you get this. But which is the more important problem to solve? And that's probably where our disagreement comes in. Okay.
Forget the last part. How do you explain the frequency? How do you motivate user-defined literals?
Ask that again.
Yeah.
Yeah, so forget my last part. I agree the problems, whatnot. But the question remains, how do you deal with this blunting factor that I just mentioned, which is in many applications, constants are few and far apart and usually grouped. How many constants can you tell me, like off the top of your head? Like, you know, the most subtle I know is the SOFA constant, which is kind of a cool thing. You may want to bing for it, Google, whatnot. So anyhow, so how do you explain this? How do you justify this in front of this attack? Which is, I'm saying there should be not many constants, so why do you make it exceedingly easy to define such?
So I look at user-defined literals as, and I'm not sure I'm answering your question here. I look at user-defined literal as being much more important because it does serve a need in terms of matching the ability to create different kinds of literals. Okay, I don't view this as being. If this was easily solvable, I would take the solution. As it turns out, it wasn't easily solvable. Okay, so I don't want to take up too much time, but we can probably continue the discussion at some point.
We can. There's going to be a panel to
Thank
end
you.
the day, so there'll be lots of destruction, Andre. But you're going to be on the panel, man. Hey, we're going to
let's
take a
stop
break. Go quick. Save your question for the panel, man.
Okay, thanks everybody.
Michael, great job.
Thank you.
Awesome job.
Thank you.